Again, so after yesterday's excellent class, Mitali will now tell us in much more detail the routing algorithm, and please ask as many questions as you can.
Thanks. Thank you, Edith. So today I'll be talking about fault tolerant routing protocols. Using HDX.
It is the crucial word. Tolerant.
Oh, yes. Yeah, this is the crucial one. Okay, so just as a recap, yesterday we saw that if a graph G has these fault tolerant protocols, then we have a reduction from any 2 CSP to a 2 CSP only that preserves the soundness. So then the goal was, can we construct fault tolerant routing protocols when G is an HDX? Okay, so today I'll be giving you guys some background on protocols, like what does it even mean? And some of the motivation why this problem was considered in previous works in distributed computing. Then I'll tell you how to build protocols against a random adversary. So, fault tolerant protocols. And then we'll build these protocols against worst case adversaries. Okay, so let's start with a very important problem. So there is one, this is called Byzantine agreement. And this was considered in the 80s. So there is one army. And they want to decide whether they should attack or retreat against another fast approaching army. And each of them has an opinion. So maybe this person wants to attack, this person wants to retreat, etc. And the goal is to decide on a common thing. Should we attack or retreat? Because if half of them attack or half of them retreat, they're going to not succeed. So the goal is to decide if attack or retreat, and all of them should decide correctly, like decide on one opinion. And if all of them want to attack, then the opinion should be that they attack, the outcome.
It doesn't have to be majority, right?
Yeah, so the hard part is that initially half of them could want to attack and half of them could want to retreat. But finally, they want to decide on a common outcome. Okay, so what would be one protocol for this problem? So a protocol is something that's designed ahead of the opinions. So one protocol could be that in the first round, everyone sends their opinion to everyone else, and then so on. And then each person first sends their opinion to everyone else. And then every person receives, every person computes a majority. If there is a overwhelming majority, otherwise, let's say 99% is the same. And then outputs that, otherwise you just output but retrieved. So this is one protocol. But now we have a twist. Some parties are Byzantine, so they are going to deviate arbitrarily from the protocol, and they are going to want to actually make, behave adversarially, in the sense that maybe they are spies from the other army. So now they will, maybe they know that half the people want to attack and half the people want to retreat. So to half of them, they will send attack, and to half of them, they'll send retreat. So that will like flip the opinion. So if you just did this protocol, the outcome would be that half of the people attack and half retreat. So this doesn't work immediately. So Lamport et al. Showed how to build a polynomial in n round protocol to solve this problem. That can tolerate up to n/3 malicious parties. So this means that at the end of the outcome, all the parties that are honest are going to go with the correct guarantee. Okay, so this is good, but what if now you have another twist?
So let me just get a sense. This corresponds to vertex faults.
Yeah, this corresponds to vertex faults.
Okay, because the communication links are
Yes.
okay as long as they don't have the Byzantine parties involved.
Yeah, exactly. So yeah, this twist has vertex faults.
And one more clarification, this is on the complete graph for now? Or?
Yeah, so here each party can communicate to every other party. And now the second twist is that what if each party cannot communicate to everyone else? And this was asked by Ward, Pippinger, Peleg, and Upfal. So here maybe what we have is a communication graph. So maybe the parties can all communicate with each other, but let's say something like that. But every party cannot communicate.
Is the whole graph known to every party?
Yeah, so the graph is going to be known.
Not so important, right? Because you only send to your neighbors.
This is important, I think, because yeah. So okay, now I'll state the goal. So how would we solve this problem, or let's say any other problem in distributed computing? So their observation was that let's first try to just build routing protocols. So what if this party wanted to send a message to this party? Let me try to first fix in advance how will I send a message from here to here. So between all pairs of units. And let's denote this by the set, let's say RUB. And if whenever U wants to send a message to V, you instead, maybe there's no direct link, but you can just use this protocol. And this protocol is again a similar kind of protocol. It's a set of rules where you decide in advance that you will send a message. So example of RUV could be that U sends a message to one of its neighbors U1, and then you send another message to U2, and then finally it reaches V.
All non-malicious actually. They know also the routing protocol is good, right? We assume they know.
Exactly. So first we build all the routing protocols because everyone knows the graphs. So all the protocols are decided in advance. And then now we can just simulate any protocol on the complete graph. So whenever, let's say this guy wants to send a message here, you just use the protocol.
So there's also a global clock that everyone knows which iteration.
Yeah. 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 So now instead of the complete graph, you'll have these wavy edges where whenever you want to send a message, you just implement the whole protocol according to the clock. And let's just say that all the protocols run in the same number of rounds without loss of generality. So you'll have these things. And now if you wanted, again, to solve Byzantine agreement and still tolerate malicious parties, it must be the case that the protocols themselves are fault tolerant, because otherwise you can't hope to solve it. So let's say we have all these malicious parties. For convenience, let me draw this as malicious. And we have basically now we have the complete graph. So how would you, why would, once you solve get fault on routing protocols, why would you be able to solve Byzantine agreement, for instance? So maybe there's one honest party here, and then it gets surrounded by the Byzantine parties. But the fault tolerant protocols will ensure that actually maybe some parties are malicious and then some are honest. Maybe they get cut out from the rest of the graph. But most of the parties here can still communicate perfectly with each other.
Sorry, so at the end of the day, is the guarantee still that you're getting that all the honest parties agree, or now it's like 90% of the honest?
Yeah, exactly. So that's a great question. So if you have a sparse graph, one vertex could get surrounded by Byzantine parties. So you can never hope to get that. So you will give up on some honest parties. So what you get is almost everywhere. Byzantine agreement.
So quantitatively, what does that mean? How many people need to agree?
Yeah, so quantitatively, let's see what you're asking for. Okay. The goal is firstly to get the goal for R, the set of routing protocols. You want that firstly they are all efficient. In the ideal world, you should hope for something like polylog n, rounds of communication and like the amount of work done to implement the protocol. And secondly, you want fault tolerance, which is something like if, let's say 10 to the minus 4, which we call as epsilon throughout the top. If epsilon fraction parties are malicious. At most, some other constant fraction, let's say 0.1 fraction. So at most all but 0.1 fraction of the parties can communicate perfectly. So some of these are going to be like 10 to the minus 4, and then additionally you give up on 0.1 fraction. So the rest of the 0.9 fraction of the people can communicate via these protocols perfectly. So that's what we want. And their goal was to also have that G is constant. So kind of this is what we mean by constant tolerance and constant degree and efficiency throughout the talk.
So in the actual theorem, is epsilon and the 0.1 like actually also scaling down with each other?
Yeah.
Mhm.
Yeah. So usually epsilon, this will be something like epsilon.
So even linear.
Yeah, I guess depends on if you do all the Markov inequalities correct. Okay, so this was the goal for in that paper. Okay, so now let me go to our setting that I described yesterday. So actually, instead of considering like all-to-all communication, we'll just fix on like doing this communication for a fixed or an arbitrary permutation of the vertices. So the model is that you're given a graph G and some arbitrary permutation. Phi. And you want to design routing protocols. RU to IFC. That again satisfy efficiency. So the notion of efficiency we'll care about is that any vertex throughout all the protocols it does around polylog and computation. So this is slightly different, but in our setting, both these notions are satisfied. So every vertex performs polylog and computation across all protocols.
So this means that every vertex has access to the permutation
Yeah.
and like what? Trying to ask the question. Like suppose you're like at step I and you have like this vertex U.
Yeah.
And so based on what it sees on the permutation, it's supposed to calculate by itself what is the
Okay, so it's a easier goal than that. It's like G is known, the permutation is known, and then globally, like you can come up with a route, all these routing protocols, and then you give the protocols to all the vertices. So they are not deciding on the fly. Yeah.
But like when you say computation, so like computation is something like doing correction to the messages they got or something.
Yeah. So this is what computation means is one proxy for computation is the number of messages any vertex receives or sends throughout all the protocols.
So he knows who to send is not part of the computation.
No,
It's just how to compute the output from the input.
yeah. Like suppose it received n messages, for example, here, the computation a vertex did was O of n.
And was this somehow the same in the DPPU model too? Like
Yeah.
was the set of R, okay, so R was computed globally.
So this means also that the routing does not depend on the message. You're always going to pass the same thing. So only it's,
Exactly, yeah.
Okay,
So these are protocols that should be, should send, basically, this protocol should, the goal is to send use message to pi of u. Yeah, regardless of the message, but today we can just think of bits as messages.
Tali, is the local computation done by like a vertex anything more than just like take all the incoming messages and take majority, or is it like?
Yeah, actually, today we'll just be taking majorities. So really, it's like the proxy is correct, just the number of messages received and sent. So yeah, this is going to be the every vertex across all the protocols is going to receive and send polylog messages. And of course, the
Yes, so-
second.
Sorry, sometimes like in network coding, linear combinations are very powerful,
Oh,
but I don't know if in this setting, like, has this ever become useful?
yeah, I don't know. Yeah, so, okay, and we want for tolerance. In this permutation model, it's just a tweak on that. So what we want is that if epsilon fraction of edges behave adversarially, then at most, yeah, like, I don't know, some f of epsilon, which is also supposed to be a constant, protocols fail. So now we are only going over this fixed permutation. In some sense, this is kind of stronger than that because you want to do it for every permutation.
and edge failures kind of capture the vertex failures too.
Yeah, that's a good point. So let's just see that. This is because edge failures, like you can corrupt, for a vertex failure, it can be thought of as corrupting all the edges surrounding it. So this is a stronger model for the adversary. And this is the model which was relevant for PCPs. And at the end of the talk, I'll maybe like hint you guys why, even though in the final Dwork et al, we care about vertex failures, actually even edge failures like is relevant there too. Okay, so this is the model. First, let's just do some simple computation for a random adversary. And let's fix an expander crouch. On n vertices and any permutation pi. Okay, so what can the simplest routing protocol be? So on an expander, we know that there are paths between any two vertices of length log n. So let's just use that as a routing protocol.
And do you require the routing to be low congestion as well?
Yeah, so against a random adversary, we don't, as we will soon see, we don't require any load congestion because each edge is corrupted independently.
And what about efficiency? If there's high congestion, is it still efficient? Do you assume this?
So yeah, against worst case adversary, it will matter. So I will come back to that point. Yeah, but actually for any expander G, we can find these paths so that in every layer across the time, you actually, every vertex is used exactly once. So it's possible to do this. This is a theorem of a lone chunk graph.
You need to be regular.
Yeah, but it's we can get regularity. Okay, so let's do the computation. So consider the adversary that corrupts every edge with probability epsilon independently. Okay. So what is the probability that the protocol RU2 R5 of U fails? So this is simple. We can assume all these edges are distinct. So we'll just get that this is going to be 1 minus the probability that all the edges succeed. So that's going to be this. And this is going to be 1 minus 1 over n to the epsilon. So against even a random adversary, if you just chose paths, almost all the paths are going to fail with high probability. So each path fails with probability close to 1. So how can we improve this guarantee? Like, can we take a better graph G where this routing is more robust? Okay, so a graph. What if we just took the expander graph, but at every node we just added cliques? So this is the expander graph you have. Like, let's say this is a tree-like expander. But every node you replaced with D vertices. And you added a clique between them. And every edge you replaced with a complete bipartite graph. So now let's like build a more robust protocol for this graph using that protocol. And when we do the calculation, we'll see that the guarantees we have against a random adversary are much better. So what is going to be our protocol? Firstly, let's say you wanted to go from a vertex U1 to pi of U1. So U1 belongs to some clique here. And pi of U1 belongs to some other clique here. So firstly, on the original expander graph, you find a path of length log n. This is the clique of U1. But now, first U1 can transfer its message to everything in its clique. But now when you go from here to here, you do not transfer just one message. Like instead, we can use the complete bipartite graph between these two cliques. So instead, what we could do is that every vertex here actually sends its message to all the D vertices. And now every vertex here receives D messages and takes majority. So and then you keep transferring in this way until you reach here. And then finally, all the vertices in the clique of pi of U1 send its message to pi of U1. And pi of U1 takes majority. So let's just calculate the probability that this succeeds against a random adversary. So again, the probability that this routing protocol from U1 to pi of U1 fails is going to be at most exponential in minus d squared. So this is coming from the least square edges here times log n, just kind of like a union bound. So let me elaborate on this. Okay, so let's look at the first step. Since you have random, each edge is corrupted independently with probability epsilon, with probability at most exponential in minus d, or yeah, or actually at least 1/4 vertices. Yes, sir. At most 1/4 vertices will receive the wrong message. So assume U1's message is 0. So in the first step itself, firstly, some vertices can receive 1s. But 3/4 of the vertices, yeah.
I'm assuming that epsilon.
Yeah, we are always assuming as epsilon is like 10 to the minus 4, 10 to the minus 8. Yeah. So I will ignore like constant factors in the Chernoff bound. So this is what we get in the first step. And now let's do the second step of the analysis. Like assuming that the first step looks like this, all these vertices, 3/4 of these receive 0 and 1/4 receive 1. Step 2. Let's do the transfer from here. So with probability 1 minus exponential and minus d squared, there are d squared edges here. At least let's just say like 2 epsilon. Yeah, at most 2 epsilon fraction of edges. Let's call these cliques C1, C2. Edges between C1 and C2 will be bad. This is just Chernoff bound. Okay, but once you have that, you get that, like at most 8 epsilon of vertices will have more than 1/4 corrupt edges incident on that. Right, this is just by Markov's. Okay, so every vertex here will touch 1/4 bad things here, and maybe 1/4 of its edges are also corrupt. But at least half of the edges are going to receive 0. So every vertex here in the top 1 minus 8 epsilon fraction will compute 0. And therefore, what you get is that this is a 1 minus 8 epsilon fraction, which is at least 3/4. So if at most 1/4 ones were here, you get that property is maintained in the second step. And so you can keep going in this way. So in this picture, what will happen is that like if you take a union round over all these events, at each step, you have 1/4, at most 1/4 ones. And then finally, you have at most 1/4 ones here, and BioFew receives the correct message.
Why did we need a clique there? Because like the vertices within that group are not communicating with each other, right?
Yeah, exactly. But we need a clique in the final step. So that's the only place we are using a clique.
Why do we need a clique in the final step?
So these vertices will get the message, but you have to transfer it back to a vertex here. Like it has to compute a majority vote. Yeah, but it's used very minimally.
Actually, but like can't the majority vote just be computed from the click that came before?
Yeah, but okay, yeah, that's kind of used very minimally. So anyway, we are paying in like these square edges between the things, so we can just slap.
Sorry, just to make sure I'm understanding. Pedantic. The first step fails with probability e to the minus d, right? So should this be e to the minus d plus e to the minus d squared times log n?
Yeah, actually, okay, so let's just like make it e to the minus d times log n. Yeah. So, okay, so now this is nice because now we can set so we can set d to be like 100 log n. And what we get is that the first protocol succeeds, or any protocol I succeeds with probability 1 minus 1 by log n to the many. So now we get the reverse actually. So only 1 by polylog n of the protocols are going to fail. And this is under constant fraction of random corruptions. This is but we have to deal with worst case adversaries. So can anyone see how a worst case adversary can kill all the protocols?
But right for the first,
Sorry, what?
right for the first, all the edges coming out of.
Yeah, exactly. So you can just take 1 by log n vertices that hit all the protocols and like destroy all the vertices there. All the edges on those vertices.
By the way, the example you discussed for expander graphs,
Yeah.
can that be made into like a lower bound proof that there is no routing possible on expanders?
Yeah, that I was going to mention that as a open question. Like, I don't know if there's any better routing possible on expanders. Yeah. But basically the hard, like a worst case adversary. Is going to do the same thing that adversary would do on a expander graph. So it can pick 1 by log n vertices, fraction of vertices that hit all the paths, all the paths on the expander graph, and then like fill all the edges on these vertices. Okay, so this is still just 1 by log n fraction of corruptions, but we are not able to send. So the observation is, why is this happening even though we have cliques in our graph? This is kind of happening because the cliques are disjoint. You can corrupt a few edges, like you can corrupt epsilon fraction of edges, and simultaneously this corrupts epsilon fraction of the cliques. Cliques or like complete bipartite graphs. So complete bipartite graph is corrupt. We say it's corrupted when it has more than half fraction bad edges. But since all of these things are disjoint, we are losing out. Okay, so one way to fix it would be to have many overlapping cliques. And with the property that if you corrupt epsilon fraction of edges, then only some very small fraction like polylog and fraction of cliques are corrupted. Again, by corrupted, I mean that they contain more than half fraction of bad edges. Okay, so, and another thing that, this is one property we need. Another property we need is just similar to what we had here, like we have a expander graph over cliques. So that whenever you want to send a message, you always send it through the path over cliques. This is already satisfied with this by this graph, but this is not satisfied. So we want these two, but simultaneously we want the degree of the graph to not be too large. For example, the complete graph has both these properties, but it does not have degrees. And you might wonder why we want degree, because in our PCP application, we didn't have degree. We only wanted the small amount of computation. But if your degree is large, you must use all the edges in the graph. So automatically the amount of computation a vertex does is large. It's going to be proportional to the degree of the graph. So we want degree of like polylog n.
What do you mean you must do? I mean, I thought it's more about diluting the constraint if the degree is too large.
Yeah, so yeah, so in this application, we care about the work, like the computation done by every vertex in the protocol. Otherwise, you blow up the alphabet too much. And if you have large degree, then the computation done by a vertex must be proportional to the degree. So it must be, so if you have a complete graph, like you cannot embed CSPs on the complete graph without like blowing up the alphabet by exponential. Yeah. So, but like degree is basically a proxy of the computation done by a vertex.
Sorry, Mitali, can you explain, like, I don't know, it's really fun like this also. Like, if you corrupt an epsilon fraction of edges, can't I just pick an epsilon fraction of cliques? Corrupt all edges within those cliques?
Yeah.
Globally corrupt an epsilon fraction of cliques and epsilon fraction of edges.
Yeah, so this cannot happen. For example, like if you just took a graph power, there are many overlapping cliques. To corrupt one clique, it can be that when you corrupt like 1 by log n fraction of the clique, they corrupt all the vertices. Right.
But corrupting a clique doesn't mean it's corrupting half the guys.
Yeah.
Right, so you pay a lot of edges to corrupt one clique.
Sure,
You
sure,
can't
if I
just-
corrupt only a fraction of the clique.
It's an epsilon divided by number of edges and clique.
Like
Yeah,
they're not
cliques-
constant.
They're not.
The cliques have actually like log n squared around like polylog n edges, or a lot of edges.
Also, sorry, I still don't understand the comment about the needing to do computation corresponding to the degree.
Yeah, actually,
Why
I
are
can
we
just like
forcing-
formally write that down, maybe because that's slightly confusing for what I said. So what I mean by this is that in our protocol here, like, oh, we'll write it here. So we have all these protocols. So if you don't, like across all these protocols, suppose you didn't use some edge. Let's say you used only epsilon fraction of all edges. Like somehow your protocol didn't even send a message across some edges, then you can just corrupt epsilon, adversary can corrupt epsilon and destroy all the protocols. So you must use a lot of edges. And once you use a lot of edges, a vertex must be sending and receiving D messages. So you want the degree to be small. Yeah.
First property, you're going to use like some sampling property of like cliques and edges.
Yeah, exactly. Okay, so what are the graphs that satisfy all these properties? So these are high dimensional expanders. Okay, so these are graphs that contain a lot of cliques that sample the edges well. So let's write a graph in a weird way. Like let's first write all these vertices in this layer and call it x1. Then for each edge, you put in a point here. Yeah, so these are all the vertices. And then we want cliques in our graph. So you keep adding cliques in every layer. So in the third layer, you put in all the triangles in G. And you keep going until you hit we'll take D equals log x. So this is a key.
This leaves us the D, the clique.
Yeah, exactly. So this D corresponds to the cliques that we had in the, oh, I erased that, but the previous graph. But now we'll simultaneously have the first property. It cannot corrupt a lot of the cliques. Okay, so what are the properties? Okay, so one property is that G is an expander graph. So this is with the second eigenvalue is going to be around 1 over D, something like that.
So this is a weak expander, but it's okay for you to get about a diameter or something at the end.
Oh, this is the lambda, like the second eigen, oh, sorry,
Oh.
the adjacency. I mean, really, because this is not really needed, but because we have D, so we get, and yeah, I mean, all we need is kind of like 1 over 100 actually. Okay, and then we have the expander graph over cliques. So what do we mean by that? So the graph GD, whose vertices and edges are, I'll just describe here. So the vertices are just going to be on the cliques. And you put in an edge between two cliques. So edges are going to be between two cliques for which the intersection is around 100. So we don't really have like complete bipartite graphs between the cliques, but I will show you that this is sufficient. So this is the graph, and this graph is also an expander graph. Roughly the lambda 2 is going to be like 1. And third property is going to be this sampling, which is the first property. So if you take a clique, like suppose you corrupt for every epsilon fraction of edges corrupted. If you took a random clique from here, then the probability that C contains more than 2 epsilon fraction of bad edges is going to be at most x in minus 50. And this was actually shown very recently by Yota. So this kind of answers your question.
That's why you take log n squared instead of log n.
Yeah.
And if they improve their theorem. then-
Yeah. And the degree of these graphs is going to be, it's some computation, but it's going to be like exponential in d squared or something like that. So it's going to be 2 to the polylog log n, which is actually greater than polylog n. So, but I will tell you how to get. But first, let's see how we get a protocol on these graphs. This is a workout.
This 4 would have been a problem even if Yotam and Max improve their theorem, right?
Yeah, this would be still a problem, like the best thing you can get.
This is like the problem I told you about, where if you prove Chernoff, then it proves 2 to the d squared is the best. You're still screwed. If you prove you can get 2 to the d, then you can't get Chernoff, so you're still screwed. No matter what you prove, you're still screwed in terms of this getting.
With this application in mind, or you had other applications?
Also, also PCP, like you can't get soundness one over. The best you can get is 2 to the root log n, like 2 to the minus root log n for the same reason. Okay, you can never get a concentration and the correct degree trade-off that you get from like expanders. It's always quasi poly instead of poly. I can explain it.
Yeah, maybe.
So what we can show is that given G as above, and any permutation costs. There exist protocols. With that are efficient. So work done by every vertex is at most 2 to the polylog log n. And fault function. This is like can tolerate constant fraction of edge corruptions. Really, the analysis is going to be just very, very similar to the random case, except that now we can do it in the worst case. So what will be the protocol? For every vertex, we'll choose a few cliques that it is part of. So that in the first layer, you have that every clique appears once. So this can be arranged. These are the same cliques that you chose over there. And now let's use the same recipe for building the protocols. So first, we want to like transfer a message from clique to clique. So first we build paths using the expander graph on cliques. So think of these as vertices in the expander graph. And now we build like log n length paths. Where now each of these is going to be an edge in the graph GB. So this is the thing. Yeah, so we do it for every thing here. And now the properties we have is that adjacent cliques have a good overlap. So adjacent cliques intersect in D over 100 vertices. Right, that's how we build the paths. And just we want like vertices to be covered almost equally. So we will also ensure that in every step, every clique is used exactly once. This we can get by this theorem of Alone et al. Actually, it's an interesting question that their theorem is not constructive, so we used a relaxed version of this, like an algorithmic way to do it. Yeah, but let's just go with this property. Okay, and now we are just going to, like the protocol is what we've always done before. Each vertex will send its message to the clique over here, and then this clique will send a message to the smaller intersection between the two adjacent cliques using majority. Then this clique will again use majority and so on. So
Just to say, like in high-dimensional expanders, each click is a face, and we're doing a high order random walk on the D faces to small faces.
yeah, so this part is like a walk over the cliques. So it's like a walk in that
So this is like D to D over 100 and
and
then
then back up. Yeah. So it's kind of like the expander, like the original routing protocol would just have done a walk over G. But instead, when you go to the higher faces and do a walk over there using majority votes, it gives you more robust protocol.
Okay.
Yeah, so protocol is just using majority votes.
Would you have gained anything if you like use the swap fork? Like you'd go from D over 100 to D. Like if they form together with like D over 15.
Yeah, you could have done that. That maybe that would have been, but would they have any? There will be a bipartite graph between them, complete bipartite.
Yeah, like
Oh.
you connect two like small cliques if they together form a big clique.
Oh yeah, that actually would have been better than doing this. This is analysis that would be exactly analogous to the analysis we did there, where we had a complete bipartite.
I mean, the spectral gap of what Yatan suggests is much, much better. Where you
Yeah.
had 1/100, and there you would have 1 over polylog. Or whatever you had globally.
Yeah.
even lambda 2.
Lambda 2, I meant.
So it's like you're only using lambda 2 to like say something about the path length, right? Not necessarily.
Yeah,
the-
it's only used to get these paths.
Yeah, so it's not
So it's not
Yeah. Actually, yeah, so this Alone paper and the algorithm, it's just like some finding shortest paths in graphs. So yeah, works as long as maybe it's 1 over 100 lambda 2. Yeah, so let's just like do a very quick analysis of this protocol. We'll just
The graph case where you planted the expander and you have clouds with cliques.
Yeah.
You could view, and then you put like complete bipartite things between the cliques. In some sense, you do have an intersecting path of cliques using those, but there's no concentration. Is that?
Yeah, exactly. So we had like 3 properties that we want. We have an expander graph over cliques, but we don't have any overlap. So if you corrupt few epsilon fraction of edges, you corrupt epsilon fraction of the complete bipartite graphs.
So there is overlap, right? So you start like entirely in the first guy and then some subset of the 2 guys that are connected and then entirely the second guy. Doesn't this give you overlapping cliques? It's just, maybe it's not an expander.
Wait, which graph? Like in the random, I can explain it later. Yeah.
Offline, sorry.
Also, I have like unrelated question. So DPPU also had a solution to the routing problem.
Yeah, actually, yeah, let me mention that. I forgot to mention that. So DPPU actually just did expander routing. At that time, actually, they didn't even do expanders. They used these butterfly networks, which are not expanders.
Because this is from what year?
86.
86.
Oh. Okay.
Yeah, and then the next paper of Upfal was like, oh, there are these expander graphs which have compressor properties, and they cited LPS expanders.
But I'm a bit confused. Didn't you say that routing on expanders was hard? Oh, I see. Is it because of the edge versus vertex failures?
Sorry, I didn't. So this is something I mentioned yesterday. So the DPPU actually only got tolerance up to 1 by log n. And one thing I didn't mention is like the later works of Jayanti, Raghuram and Vyas. So they improved this tolerance to constant. And what they did was the similar graph that I drew, like you replace by cliques. That's tolerant against a random adversary. And then you overlay the same graph randomly on itself. Like you permute the vertices and just make copies of it. But when you do all the analysis, like this can never be tolerant against edge corruptions. So really for edge corruptions, you need like some systematic overlapping cliques.
So the thing is, when you overlay, you have an expander, now you overlay it over, some random other expander. So the vertices match, but the edges are now in completely different locations. So when you do vertex corruptions, it's the same vertex it's corrupted.
Yeah, exactly.
When you do edge corruptions,
I see.
Yeah, so it's like if you're tolerant against a random adversary, and then when you overlay it, you can do a union bound against vertex adversaries. But you increase your edge budget, so you can't do union bound.
So that loses you 1 more log n then? Like you do
that
log n things?
Yeah, exactly. You get like polylog n degree, but you are tolerant against constant fraction of worst case adversaries. Yeah. So we can now do the analysis. Okay, so now instead of just doing analysis path by path, we look at all the paths together. So let's look at just the first time step. And these are all the cliques. I can kind of assume, just by giving up something in Markov's inequality, I can just assume that most of the cliques have like 1/4 ones. Let's say you started out with the message all zeros. So most of the cliques have like 1/4 ones on that. And the property we'll maintain is that this always holds. Okay, so first, thing is that what are the fraction of cliques that contain more than 2 epsilon fraction of bad edges? We know it's small. So let's say these are some of the bad cliques. Like this is an exponential minus root fraction of all the cliques, and maybe they contain too many bad edges, so we give up on them. But all of these cliques, they contain like the good cliques. Contain sorry, actually. Here we have like we pass to a smaller clique and then we pass back up. So slightly different. But yeah, okay, look at all the cliques here, which in the first layer, which contain too many bad edges, and we gave up on them. And then let's see these cliques. So good cliques contain at most 2 epsilon fraction of bad edges. So for example, let's take this clique. It contains at most 2 epsilon fraction of bad edges. So when you go to some smaller subset of it, the edges between all these guys, this is going to be at most like 200 epsilon fraction of bad edges. Between, let's say, C1 and C2. And yeah, let's redraw it. And it's just the same thing again. Like this is going to be like 1/4 things which are the wrong message. And then this is going to have like 200. Between these two, there's 200 epsilon bad things. So there's going to be at most some 800 epsilon fraction vertices that have more than 1/5 fraction bad edges incident on them. But the rest of the vertices will compute the correct majority. So you have maintained the property that for all these good cliques, like 3/4 fraction has zeros on them and 1/4 has ones. And then you just do this again for the next step and so on. So for the next step, you maybe lose more exponential and minus root d fraction of the protocols, and you keep losing that. And then you do a union bound over all the rounds. So.
Sorry, one tiny thing. Is it 200 or like 27? Like, not a big thing, but it's more like I was thinking the edges grow square to the sides. Is that
So actually, I mean, it's like epsilon fraction of all the edges is bad. So this is going to be like 1/100 fraction of all the edges, right?
it's 1/4
Or maybe
4, but
No, is it about, so we are counting the edges in the bipartite graph, right?
Yeah.
So it's like D
Oh,
versus,
see.
so it is
over 100.
Okay, cool.
Yeah. Yeah. So okay. And you just do a union bound. So it's basically the same analysis that you had for the random case, but now against first case.
By the way, I forgot to tell you that you can take a break if you want, or you don't have to take a break if you don't want.
So actually, I just wanted to, kind of end the proof of the lemma, that lemma, and remark on something. So. So we have that at most exponential and minus root d fraction of cliques fails at every time step. And then we can use a union bound. Across all the log n time steps to get that at most x log n cliques protocols. So if you just calculated this, we had like take d to be 100 log n squared. This would just give you that, you know, fraction protocols fail. So we had constant corruptions, but if all the cliques were guaranteed to have this nice initial property, then you get that actually only little of one fraction of the protocols fail. And this can be used to get an amplification for PCPs. Like you can amplify the soundness from 1 minus 1 by polylog n to constant. So just the initial prover will kind of guarantee that this property holds. It'll just check each clique first. But yeah, that's just an aside. Okay. So this is good. But as we saw, the degree of this graph is going to be 2 to the polylog log n, and therefore the work complexity is 2 to the polylog log n. So how do we go down? We reduce the work complex. So the kind of observation is that really we didn't require cliques to do this transfer of messages. What we would have been okay with was some kind of dense subgraph, let's say of constant diameter, which is also an expander graph. So but we want this in addition to the, instead of the cliques. But of course, we also want expander graph over all these dense subgraphs. Again, the sampling properties. By this, I mean that if you have a few bad edges, then most of these dense, only little of one of the dense subgraphs contain too many bad edges. Okay, so what are the other dense subgraphs in a high dimensional expander? Actually, it turns out if you just took any vertex's neighborhood, that's a dense subgraph. So this just means that you take a vertex and look at everything it's connected to. And this subgraph has a constant diameter. And itself is an expander. Okay, so more formally, for this clique-to-clique protocol, we had parameters d equals log n squared. This is the largest cliques in the graph. And the spectral expansion, like lambda was around 1 by. But instead, we can take different high dimensional expanders where D is a constant, but the spectral expansion is very good. So the spectral expansion is going to be 1 by polylog n. So by lambda 2, I mean that lambda 2 of G itself. So by this, I mean lambda 2 of G is 1 by polylog n. And lambda 2 of any vertex neighborhood, which is actually called links in the high dimensional expander. So lambda 2 of links is also 1 by polylog.
So you reduce the degree and lambda to simultaneously?
So because D is
D is not the degree.
oh, D is the dimension.
Oh, okay.
Yeah, this is the dimension. So these kind of high dimensional expanders. So in general, the degree of the high dimensional expander is equal to basically 1 over lambda 2 to the dimension. Roughly. So this gives us polylog n degree. And so I won't analyze like the protocol, but roughly it's going to be the same protocols. I can just tell you what it will look like. We call this the link to link protocol. So you would just choose paths over just the expander graph G first. So you'll just choose paths U1, U2 up to pi of 1. And then similarly, but again, you're not going to actually send the message along the path, but you're going to send it along the links. So U1 will send its message to its link or its neighborhood. And then this whole message will get transferred to the whole link here. So these links will have an intersection, not a very large intersection, but this is the link of U1 intersect the link of V2. But, and again, sorry. So what we had done in the click-to-click protocol was that every vertex here took a majority of all the vertices in the previous round. But we can still take majority, but now there's no direct connection between them. But instead of like direct connections, we are just going to have every vertex here will be connected through some constant length paths to every vertex in the previous round. And it will take majority over those paths. So the final analysis will use some sampling properties. And I can just list down the sampling. One is that if most epsilon fraction of edges in G are bad, then at most 1 by polylog n fraction of vertex neighborhoods or links have greater than 2 epsilon fraction of bad edges. Actually, this is true of any expander graph. We have not really used the high dimensional expander property yet. This is just like a sampling property that you would get for bipartite expanders. Or yeah, just expanders. But additionally, what we have to use is that inside a link, if it has at most 2 epsilon fraction of bad edges, then at most 1 by polylog n fraction of links within it have at least 4 epsilon fraction bad edges. This is kind of to argue that these small intersections that we are going through, not many of them are going to be bad. We can't really, so in the click-to-click protocol, we just gave up, we just use some Markov inequality. But here we need to use this more sophisticated sampling property.
When you say like this fraction of links inside, you mean what the edges that connect the link inside to the to all the link?
Yes, I'm like lying how exactly we use this. It'll be something like, when you construct these paths, there'll be some vertices that become isolated, and we'll say that there are not many of those vertices, and then we'll use sampling to say that not too many of these intersections have many bad vertices. Yeah.
So what do you mean by the first property is true for normal expanders? Like how do you define the link in the?
Oh, link is just a vertex neighborhood.
Yeah, okay.
That's the definition. So it's always true.
When you say edges inside the link, do you mean the edges that connect the neighbors to the vertex, so connect the neighbors among themselves?
Oh yeah, maybe I can be more formal. Oh. So what I mean is that if you took an expander graph, but then wrote it in this way, where on this side you have all its vertices and on this side you have all its edges. Like for every edge you have a vertex unit. And some of these are bad. Then yeah, so connect a vertex to an edge if that edge is incident on the vertex. Yeah. So only 1 by polylog, or sorry, 1 by lambda 2. So lambda 2 of these vertices will have like more than 2 epsilon.
Yeah, what's confusing me, I understand that, what's confusing me is in the picture link to link. Can you say it again, like a bit more exactly what you're doing?
Oh.
I was thinking you have a path from U to pi of U.
Yeah.
And then from U1 you move to U2. And in U1 has all these neighbors, V. U2 has all these neighbors. And there are some neighbors that are joined both to U1 and U2.
Yeah, so that's the
This
link
is
of
like
the
the
edge.
link of the edge U1, U2.
Yeah.
And that's like the smaller link. So you're moving from the link of U1 to the link of the edge U1, U2.
Yeah.
And you move from the link of the edge U1, U2 to the link of U2.
Yeah.
Okay. So then when you draw these circles, I'm supposed to think of the neighbors of U1 and like as vertices.
Yeah.
What are the edges that are getting corrupted? The edges among these neighbors?
It's the edges among the neighbors. Okay, yeah.
That's
You're right. Yeah. So in this graph, you would actually connect U1 to the edges like amongst its neighbors. Okay, yeah, so this won't be true of an expander. Then. Yeah.
Yeah, so
Yeah.
just to clarify, so what are we doing? So we are connecting, who is talking to who, like in the routing protocol?
So in the routing protocol, first, U1 will send a message to all its neighbors. So this is the neighborhood of U or the link of U.
Okay, so these are vertices now?
Yeah, these are all vertices.
Okay.
And then each of these vertices will send a message to, this is now the link of U1 and U2. So each vertex here will send a message along a short path to every vertex here.
So the length of this path is log of the size of this neighborhood?
No, we'll just give up. It's going to be constant diameter. We'll like give up on a few vertices. Like it's going to be like 1 over epsilon. For some epsilon we choose.
So how do I know, yeah, can you explain that part? Like, we have this N of U1, it's an expander.
Yeah,
And inside of it, there's a smaller subgraph,
yeah,
which is the link of U1, U2.
yeah,
It's also an expander on its own.
yeah.
And then what are these shortcuts?
Yeah, so these short paths is something we can construct. Like we just give an algorithm to construct them just by looking at the exact structure of the link. But the link has the additional property. Maybe I can just write the exact.
That's where the diameter comes in of the.
Yeah. It's that for every vertex U in the link, in some link L, U has an at most 1 by epsilon length path to 1 minus epsilon fraction of the vertices. So technically it's not like constant diameter, but we just give up on some very far vertices. And this is okay because finally we are taking majority votes. Like we don't want to, like when you just take a majority over most of these vertices and you give up on some very far away vertices here.
You need to give up though, I mean.
Yeah. Because the diameter of this link is going to be proportional to the dimension.
Which is a constant.
It's a constant, but we cannot lose factors proportional to the dimension. We are thinking of like epsilon being much larger than 1 over d.
Much larger than that.
Yeah.
That's because of some other reasons?
Yeah.
Okay.
Yeah.
For the routing,
Yeah.
if you just cared about the routing,
Yeah. Then
without the PCP amplification,
yeah.
then this is not an issue. Is it?
Yeah.
This 1 over epsilon is the same epsilon that you're using.
Yeah, we like use root epsilon, something like that. It's going to be the same, related to the same epsilon tolerance.
Right, but like the reason that you want this like 1 over root epsilon is that you're going to do a union bound on all these paths.
Yeah.
And say that like about the root epsilon.
Yeah, so exactly.
We'll have a corruption.
Yeah,
And then you're like going to treat every path like this as an
edge, exactly. Yeah.
What I'm kind of confused about is, can you have dimension which is like 3? Just vertices, edges, and triangles, that's it. And then,
Okay, so that's not fine just because we want like these paths over the expander themselves, like, and all these graphs are like d-partite. So the this expander path thing works only over like we need a two-sided bound for that to work. So we need D to be large, but D should be like 100 or something.
I mean, you're thinking about a concrete construction of a high-dimensional.
Yeah.
Maybe we can take it offline, but I just, if you were guaranteed the two-sided expansion, on two.
Yeah, then it would be fine.
Then it would be fine, so
Yeah,
you don't need this dependence on the epsilon for this.
Yeah, yeah.
Okay.
It's just like for this concrete HDXs that we work with. Like if you had a two-sided HDX, then everything would be fine.
Right, but I guess to get polylog n expansion, you'd need to take a polylog n one-sided dimension.
No, you need the degree to be polylog n, not the dimension.
We don't know how to construct them, okay. Two-sided, we could do.
Okay. Yeah, sorry.
Yeah, but
Allegedly, if there was such a construction, you'd be happy with dimension.
yeah. Yeah, exactly. Yeah, but basically the protocol is just that there's no direct edges, and it's what Yutam said. You take very short length paths and you just linear round over those paths. Each of these paths is going to be only like root epsilon fraction of these paths are going to be bad. So you can treat it as edges. Yeah, so that gives you like finally this gives you G with polylog and degree, constant fault tolerance, and polylog and work complex. So this is good enough for the PCP application. And like finally, I just wanted to mention a few words on the original problem of Dwork et al. So this was their problem where they needed constant degree. So one question is you may try to do this routing protocol on just a constant degree high dimensional expander, constant degree, constant dimension. It will need to have like constant lambda too, but that I don't know if that's possible. So that's a good open question. The way we do this is you just take graph products of these high dimensional expanders with themselves, something like what you do in expander graph constructions. So you take a large graph G on n vertices, which is the same graph like here, and you do a replacement product. So maybe you've heard of zigzag product. It's the easier version of zigzag product. And you do this with a smaller graph G on the number of vertices. So this is going to be polylog n vertices. And after the replacement product, you get a large graph G on n polylog n vertices, but it inherits the degree from the smaller graph. So the degree becomes polylog log n. And in this composition, if both the graphs have constant fault tolerant protocols, and the fine graph also has constant fault tolerant protocols. So this is something we show. If this and this have constant fault tolerant protocols, then so does the final graph.
Can you repeat this process?
Yeah, so exactly. So we can keep repeating this process, but every time we are just going to go by log. So how would we finally get a constant graph? So it turns out that Upfal had constructed constant degree graphs. So just expander graphs. He showed protocols on them with exponential time. or exponential work complexity. So you do this composition 3 times and then you compose with Upfal's graph to get down to constant. So it's very similar to like PCP composition. So like some open question I wanted to mention was just that, I mean, do these graphs, like composition of these HDXs give some other nice properties? Or like, can we get the protocols, these kind of protocols just on HDXs themselves?
If you did have this protocol on HDX, would there be a PCP consequence?
Yeah. So if you got like tolerant protocols on HDX, like theta 1 dimension and theta 1 degree HDX, then you should expect that the work complexity is like some fixed polylog n, right? So the work is going to be like fixed polylog n. So log n to the C, where C is also some fixed absolute constant. And this should give you PCPs in low soundness. Let's say with epsilon soundness and C of epsilon times n times log C size. So the exponent in the log n would be independent of epsilon.
I see.
But I suspect that I mean, I think you would have to use more properties of HDX. Like I suspect maybe it's not even possible for generic HDX.
Like even with the topological, like the special ones you guys construct?
So the special property, like those topological expansions not used for these protocols at all. So I don't see how that is connected.
What properties do these composed HDX have? Are they still high dimensional or?
Yeah, I didn't think too much about that.
You just think of it as a graph and the replacement
Yeah.
product is a graph.
Yeah, and then it's like a simple composition of protocols. Like you again simulate the outer protocol, but like using the inner gadget.
So if you look at the resulting graph and you try to do this majority protocol on it, it won't be the same protocol as the one you're actually doing. Because you're like doing a more specific kind of majority.
Yeah.
Is that right?
Yeah.
I think that inside this protocol, at least the original one, but I think also the other one, there's like this sampling property, which is maybe actually some kind of if and only if. Because if you had like some configuration of edges that would sample badly, you could also like ruin the protocol too. So maybe like be surprised if something like if you could still get something that has the same type of sampling from this replacement thing, then you almost got a new high dimension expander out of it, right?
Right. So you think it probably doesn't have the sampling
Yeah.
because they do a different protocol, they stick
Yeah.
it around it.
Oh, yeah. Yeah, so this composition is pretty abstract. It's like whatever protocol you have for this and this, you just simulate that protocol on the graph.
Okay, wow, thank you very much for so many details and